Y8 oscillations revisited. We learned this one in the last semester. This is a harmonic oscillator. Harmonic oscillator has two linearly independent solutions. If we substitute cosine omega t and sine omega t in this equation, we notice both of them satisfy this equation of motion. So C1, C2 arbitrary constant, cosine omega t plus sine omega t, that is a general solution. Arbitrary solution can be expressed in terms of this linear combination. We know cosine x is 1/2 of e to the ix plus e to the minus ix, and sine x equals 1/2i e to the ix minus e to the minus ix. So if we substitute in here, this one, these two are also the solutions. And this linear combination of the two linearly independent solutions is a general solution. Sure, and if we consider the mechanical problem, x is a real value always, so we can remove the imaginary part. However, it is usually convenient to use this phasor style expression in terms of complex variable, especially when we consider electromagnetic propagation that we learn soon. This expression can be recombined into a single sinusoidal function. In high school, we learned that cos, sine, negative sign is the sum of cosine alpha plus beta. In here, we have introduced C1 squared plus C2 squared pulled out, and we can define this one to be cosine of delta, and we can define this one to be sine of delta, because the sum of these squares is always the sine squared delta plus the cosine squared delta is identical to 1. So we have positive sign in here. The result is the cosine omega t minus delta. So this one has two independent parameters. In here, we have two independent parameters. They are mathematically equivalent expression. We can parameterize the general solution in terms of sinusoidal function, not cosine but sine. In that case, sine, cosine, sine summation has a positive sign because both of them are positive. If we know the initial conditions for the initial position and the initial velocity, then we can express the general solution as these two undetermined parameters are completely fixed. Suppose that we use this cosine expression as a general solution. First, we substitute t equals 0, then it becomes a cosine minus delta, and the cosine is an even function, that is a cosine delta. First order time derivative of this position will give you minus a omega sine omega t minus delta. Substituting t equals 0, you will find it's a omega sine delta. As we know, cosine squared plus the sine squared sum is always 1. Therefore, a can be written as a sum of a cosine squared and a sine squared, and then take the square root. Using these two conditions, we can express in the amplitude in terms of the initial value for the position and velocity completely. Sure, this delta is also expressed in terms of a tangent, and the tangent is sine over cosine, and using these inputs, we can determine the tangent delta. Therefore, tangent, this delta, can be expressed by making use of the inverse function of tangent called arctangent, That is the value. We have a point mass M is attached to the simple harmonic oscillator. The solution, okay, we can use either plus delta or minus delta. That depends. We can determine these parameters completely by making use of the initial conditions. Anyway, suppose that we use this parameterization for the solution. First of all, omega 0 is a square root to k over m. So spring constant k is determined as m times omega 0 squared. The Hooke's law, force minus kx, is a conservative force. If you compute the curl of this force, it is absolutely 0. When curl is 0, applying the Stokes theorem, curl f over a surface, open surface, then you will find it is expressed as a line integral over a closed path that is the boundary of this surface. And because the integrand is absolutely 0, therefore this closed path integral is always 0. That is called the conservative force. It is also true that f is always expressed as a gradient of a scalar function. In that case, this integral becomes a minus a gradient potential differential, and this is x partial derivative dx, y partial derivative dy, and z partial derivative dz. What's that? This is a total differential of this scalar function. So this total differential of the scalar function, evaluation of this integral is trivial. What's that? That is a u minus a u at a single point starting point and initial point, final point. However, it is a closed path. These two are the same. That is 0. So this is the complete story of the conservative force. Because the conservative force, because this one is a conservative force, and this any closed path integral of the work is 0. Total mechanical energy, that is the sum of the kinetic energy and potential energy, must be preserved every time. Substituting these results for the solution in here, we find the complete time dependence of the kinetic energy and potential energy, and they are sine and cosine. Sum of them is exactly 1. That is conserved completely. In addition, we can average over a period of this oscillation. So average means the time integral divided by the period. And this trivial integral can be done by a high school student. We know everybody knows that is a 1/2. That's the reason why the final result is 1/4 Ka squared for both kinetic and potential energy. This is a simple harmonic oscillator. In addition, we have a damping force. Damping force minus Vx dot is applied in here. If you write down the equation of motion, this is a force, and we have a restoring force. We have additional damping force. I have moved this one to the left-hand side, and then I can divide this expression in divided by mass m, then we will reach the expression like that, because omega 0 is a square root k over m. Now we'd like to solve this problem. This is called the damped harmonic oscillator. This, because of this, the presence of this damping term, it is called the damped harmonic oscillator. The solution of the damped harmonic oscillator can be found by substituting a trial solution, that is carrying an eigenvalue, frequency eigenvalue lambda as an exponential function. It is trivial to find out the time derivatives, first order time derivative brings of additional factor lambda and second order lambda squared. Sure, there used to be e to the lambda t. However, this exponential function does not have a zero everywhere, so I can always divide this out without mistake. The quadratic equation solution for the real valued case, the middle school student can solve this, but you learned how to solve this problem in every case in high school. The result is this. And this capital D is called the discriminant. This one discriminates the solution, types of solutions. If this one is a positive, then we have the sum of two real numbers. So there is no oscillation. This one is called over-damped case. The second case is a different sign, negative sign. If we have a negative sign inside the square root, your result has imaginary part. And we know we have exponential minus I something t. Aha, it is related to linear combination of sinusoidal functions. Therefore, the imaginary frequency, this imaginary eigenvalue lambda, represent the oscillating behavior. However, we have additional real value that represent the exponential minus 1/2 of gamma t. That makes the solution smaller and smaller as time goes by. This factor appears in any case. The problem is that the sign of this. At last, we have double root when this discriminant becomes a zero. That is called the critically damped case. And we have analyzed all the details about the discriminated solutions, three kinds of solutions. First of all, this one is a typical solution for the underdamped motion. Underdamped motion is have a common factor. We call it evanescent factor that decays exponentially, and oscillating factor coming from this negative value inside the square root. And this one, because this is negative, we have the oscillating frequency is different from omega 0. It is a square root omega 0 subtracted by 1/2 gamma squared. So it is a slightly smaller than the original frequency. Frequency is smaller. That means the period is slightly longer than the original period of the simple harmonic oscillator. In addition, if we compute the potential energy and kinetic energy, and sum of them, there are three curves, we can see the energy is decaying arbitrarily small, and as t goes to infinity, everything disappears. It's just like what you ride a swing. At first time is going up forward and backward, and as time goes by, if you do not apply any driving force, finally it stops. That is called underdamped motion, very, very important one. And next case, overdamped. We do not have the imaginary part. Both of them are real. Therefore, the solution has a common factor in here. However, we have additional exponential plus minus. However, this gamma prime is always smaller than gamma. Therefore, this one is a more decaying very fast. this one, because gamma prime is smaller than gamma, it can never win the game with the over coefficient. Both of them, this term and this term, both of them are strictly decreasing function. So as time goes by, this one is gone, absolutely. The typical example of application of the over-damped motion is a door damper you usually use every day. Door damper. Mathematically interesting, but we mostly never experience is that this is the application that we just have considered, the over-damped case. And a very strange case is gamma is just 2 times omega 0. We have a double root, and it is at first look, it is very hard to find the solution. However, we can reparameterize this solution x to b, factored out the common factor multiplied by something called y. And we find the equation of motion for y is a trivial equation. And the high school students know this answer is constant plus constant times time. So this is the general solution for critically damped motion. Critically damped motion. Critically damped motion when this one is satisfied. But in reality, you will it is very rare to find such kind of situation. A special case is a specific case with the vanishing initial velocity with the non-vanishing here, non-vanishing velocity and starting point in here. This is a position you can find a turning point. That's the difference between the critical damped motion and over damped motion. But our most concern is the under damped case. Here, we consider a special case that is called the driving force is applied. We can see actual solution is a blue curve. There is a difference at small t region that is called the transient effect. And the origin of the transient effect is the solution of all these damped harmonic oscillator without applied force, without driving force. When you turn on a system, for example, light, as time goes by, it becomes a stable, steady state solution. However, at t equals very small, it is deviating from this steady state solution. That is the contribution of the solution with the right-hand side 0. Mathematically, we say it is a 0 means it is a homogeneous equation. And that is a damped harmonic oscillator without driving force. So solution of this one can be expressed as a linear combination of XH, that is called damped harmonic oscillator solution, and in mathematics they call is a homogeneous equations general solution. That we already know for 3 cases. However, in general, once you know the solution of this equation by accident, let me call it you have a particular solution, a single particular solution. However, you know the solution for the homogeneous equation, and why don't we sum these two? Then operators are linear, so we have a double time derivative of particular solution plus a homogeneous equation solution, and so on. And right hand side is still the same. Aha! Even though you found a specific solution for this general equation, however, there is a contamination coming from this homogeneous equation solution that we just solved previously. Actually, some of these is the general solution of this driving force situation. Nevertheless, this homogeneous equation solution that has a special behavior as t goes to infinity, they are dying out absolutely. Numerically, it is nothing as time goes by, except at a very tiny value of time. Therefore, we expect that as t is large, your specific solution can be a steady state solution as t goes to infinity. And the solution for this specific solution can be solved by substituting the trial solution. In here, this omega should be the same as the omega of the driving force, because this right-hand side is a function of sinusoidal function of frequency omega. What happens to the case if I substitute the trial solution other than omega? Then left-hand side and right-hand side can never become identical to each other. Therefore, the solution for this particular solution must have the frequency identical to that of the driving frequency. And if we do not allow the phase difference, for example, these two are in phase, double time derivative will bring the same cosine or same sine or same exponential function equally. However, this guy, single time derivative flips cosine into sine and sine to cosine, it becomes dirty. Exponential case bring in the imaginary part. Therefore, by introducing a phase shift and removing this one by expansion, because the right-hand side does not have such kind of a delta dependence, hopefully. By the way, such kind of trial solution will indeed kill the phase difference if the phase of this complex number exactly cancels this, then this identity works. And the final solution is this cosine and sine must have a real part and imaginary part, and the denominator is just nothing but the sum of these squares, and we have taken the square. Therefore, the amplitude of the particular solution for the displacement has this kind of shape. And we notice that varying gamma and omega is the driving frequency, we have a sharp increase of the amplitude at a certain value that is very near to the frequency of the simple harmonic oscillator. This is called the resonance. And as gamma becomes smaller and smaller, this peak of the resonance becomes very sharper and sharper. If gamma is very large, the peak is very broad. It is sharp. Every day you communicate with the cell phone or you watch TV or everything, any electronic device use this resonance. When you ride a swing, you apply your own driving force by hand and your body to make the frequency of oscillation your driving frequency must fit the frequency of this pendulum. So you are every day confronting with the resonance in physics. And such kind of calculation can be done for the velocity case too. And in the case of velocity, that resonance frequency can be achieved by exactly the same as omega 0. In an electronic circuit, we usually use a current as a reference instead of a charge that is charged inside the capacitor. So velocity is equivalent to the current in the circuit. So velocity problem, when we solve the velocity problem, the resonance appears in exactly the same as the frequency of the simple harmonic oscillator. And at that time, the amplitude has explicit value that is anti-proportional to the coefficient of damping force. And the expression for the frequency in here can be found in the Y8 original version, the lecture course.